Hello, can you hear me?
Yeah.
Okay. Today is 15th August. So we'll discuss product topology. Earlier today we have discussed about subspace topology. Now we'll discuss product topology and mainly quotient topology. But for those two things we also need to discuss continuity, continuous map. And we also sometimes we need house dot property. So those are some preliminaries. So let's start. What is Hausdorff space? A space is said to be Hausdorff if you can separate any 2 points. Suppose 2 point is given, P and Q, those are 2 points in the space X. If we can separate it by some open set around P and around Q, disjoint open set, suppose this is UP and UQ, then we'll call it, sorry, okay, thank you. Happy Independence Day, everyone. So, Hausdorff space means you can separate any 2 point in that space by two open set. Okay. So let us see some example of Hausdorff spaces. First of all, R is Hausdorff, right? Real number. Any 2 point. Choose any 2 point. This is P and this is Q. You can always separate it by open sets. So take the distance and take a open set like this. Okay. You can take this radius to be half of the distance. So this is the most uh, optimal way to separate. You can extend from the on the left and right side, but this is one of the way to consider open sets. So we have just started now. There is nothing before. Okay. So this is R. In similar way, we can also separate 2 point in any given metric space. Suppose X is a metric space XD, then choose any 2 point. P and Q are two given point in the metric space. This is the metric space. P and Q are 2 point. Then how can we separate? Okay. So the way to separate is take the distance between P and Q and take the open ball. This is not a good way to put. So suppose the radius define, let r equal to distance between p and q, and we can always consider open ball around p and around q with the distance r by 2. So this is the distance r by 2, right? You can easily verify that p belongs to bp comma r by 2 and q also belongs to b by definition. And the interesting thing is that their intersection is empty. So those are some standard examples. Now let us see another example. So we are familiar with lower limit topology or upper limit topology. So consider lower limit topology R with lower limit topology. So here the open sets are given by this a comma b such that a less than b, a b belongs to real number. So those are, this forms a basis for this topology. Tau is generated by this basis. Okay, maybe tau L lower limit. Tau L is generated by this basis. Okay, this form a basis for this lower limit topology. Now can you see that we can always, okay, there are lots of students now. So can we see that we can always separate any 2 point in this lower limit topology? So as before, we can always take the same type of open set. We already know this type of open sets, those are also open in lower limit topology, right? So we can separate it by that previous open set, right? So this is for any 2 point P and Q. Just take the open ball. So here the open ball is the distance is P plus Q. So this is P plus Q by 2, and you can always take those two open ball BP with radius P plus Q by 2, and similarly BQ comma. So you can write in terms of open interval. For example, this will look like P plus Q by 2, which is 3P plus Q by 2, and P minus Q by 2. So those kind of open interval, right? And so from this you can, another way open set, you can also separate it by this kind of open set. So the same, for the same P and Q, you can choose this open set, right? You can choose this open set and this open set, that is P comma something P plus the previous one. You can also choose the previous one, and Q comma something, right? Q comma anything, Q comma infinity, this works, or anything Q comma 2Q, let's. So those are Hausdorff space. We can separate those 2 points by open set, right? By open neighborhood, we can always separate those 2 points. So those are some examples, and from here we can observe that so if x tau, consider tau and tau dash two topologies such that tau dash is finer, okay? Then so we are considering two topologies, tau dash are two topology on X. Then if X is Hausdorff, So there is a notation for Hausdorff. It is written by this T2. Hausdorff property means it is T2 property. Okay, those are actually separation axioms, and there are some kind of, there will be more T1, T2, T3, T4. It will appear later, but this is our interest. So if X is Hausdorff, then Y is also Hausdorff. Sorry, X tau, this tau is Hausdorff, then X comma tau dash, because tau dash is finer. You can always, tau dash has more open set, so you can always separate it by that previous open set. Okay, whatever open set you are using for the separation in tau, you can use the same open set, because that is also open in tau dash, right? So that's why this is obviously true. Now let us see some non-example. Three, so it is 4. So X with the topology, indiscrete topology. Suppose X has more than 2 point, more than 1 point. That is, cardinality of X is greater than 2. Then can we see that it cannot be Hausdorff? Can you see that this is not a Hausdorff space? Yes, we can see, because so the topology is empty and X. So if it has two more than 2 point, suppose A B are 2 point in X, yes, then the only open set which contains A and B are X, but X intersection X is non-empty, right? This is not empty. Therefore, this is not Hausdorff. There does not exist any U A comma U B containing A B respectively, such that U A intersection U B is empty. There is no such U A and U B. So one example which is always Hausdorff, example, suppose example 0. So tau with discrete topology, x comma tau, which is x comma discrete topology. This is always Hausdorff space, because every point is open. So for 2 point A comma B, again there is a slight mistake. For two distinct points, this is, if we choose P and Q are same, then it is not possible to separate it by distinct open set, different, that is non-overlapping open set. It is not possible. So here P and Q are two distinct points. The definition, two distinct points. Okay. We can see for let A comma B 2 point in X, such that those two are different point. Then you can always choose the open set A, because this is discrete, everything is open. Similarly B, so A belongs to A, B belongs to B, and the intersection A intersection B is empty, right? So this is always, therefore this is T2, this is Hausdorff space. Let us see some non-trivial example. Consider R with with the topology cofinite topology. the question is it Hausdorff? So let us see if it is Hausdorff or not. So let A comma B are two different point in R. Okay, such that A not equal to B. Now let us try to separate those 2 points. Okay, let UA there, let it is Hausdorff. Then there exists UA comma UB containing A comma B such that UA intersection UB is empty. Okay, if possible we are assuming this is Hausdorff. If possible, assume Hausdorff. Then there exists some UA UB containing U A comma B respectively such that their intersection is empty. But this will imply UA intersection UB complement is same as empty complement. So again De Morgan law, this says UA complement intersection UB complement. This is now complement of empty means the whole set R. But we can note that UA and UB are non-overlapping open set. So what are the open set in cofinite topology? So so the open set
complement is finite.
Yes, complement of finite. Something is open if complement is either finite or there is another choice empty. Okay, so UA complement is empty. This is not possible, right? Not possible. Why? Because this will imply
It
UA is
contains it.
whole set. So that separation is not possible. Therefore, UA complement must be finite, right? In cofinite topology. Similarly, UB complement is also finite. Therefore, intersection of finite set, this is finite, right? Both are finite. Therefore, their intersection is also finite. But on the right hand side, this is not finite. So it is a contradiction. Contradiction. This is not possible. UA must be finite set. Similarly, UB finite, so their intersection should be finite, which is a contradiction because finite set cannot be R, real number. Therefore, our assumption is wrong. Hence, this is not Hausdorff. R with cofinite topology, this is not Hausdorff. Exactly. The same argument can be applied for co-countable topology, right? So I am writing this is as A. Similarly for B, R with co-countable, this is not Hausdorff. But note, if the given set instead of R, if we replace it by X and X has finitely many points, then that will be Hausdorff, because in that case cofinite topology will be same as discrete topology. We have already seen, right? So that's why I have chosen that R, because R has infinitely many points. Similarly here R has uncountably many points. That is where the contradiction will arise. Okay, so those are non-example. Similarly, you can also check that this is also non-example. That A comma tau is given by this basis topology on R. with a topology generated by this basis a comma infinity, right? A belongs to some real number. So if we consider this basis, then again we can prove this this cannot be this house draw, because for any 2 point, what are the open set which contains this A? It will look like something, and the left hand side goes to infinity. Similarly, open set containing B, it will look like something and extend to infinity, right? So there will be always overlap. This portion will be always there. The part B comma infinity, whatever is bigger. Okay, this is A, this is B. So this B comma infinity will be in the intersection, that contain in the intersection. So this cannot be house drawn. So those are few examples. Now let us see continuity. So we'll study the property continuity later, but for product topology and quotient topology, we need this property actually. That's why I am defining continuous. Continuous function or continuous map. So consider a function f from x to y. This is a map between topological spaces. So x and y are topological space. Then this is said to be continuous. Is said to be continuous map or continuous function if f inverse of any open set. So take any open set from Y, their P image should be open in X. Okay, f inverse P is open in X for all P open in Y. So I am writing X to Y, that is actually abuse. I should always write X comma some topology tau and Y comma some topology tau dash, because we also need to see what are the topology in Y. Otherwise, open set and those does not make any sense. Okay, so those are abuses of notation, but this is the definition. So take any open set in Y and pull it here, f inverse P. If that is open for all open set in Y, then sorry, this is open set in Y. Sorry, this is okay. So take any open set in V Y V. If the preimage is also open in X, then that is called continuous map. So we already know about continuity. For example, any polynomial from R to R. Okay, any polynomial, those are continuous. Yeah. So let us see some continuous map in any topological space. Okay. So this is example 1. Let us see example 0. So identity map from X comma topological space to X comma another, the same topology. This identity map is continuous. Can you see why? Because identity inverse of some open U is same U, right? So therefore inverse image of open is open. Similarly, you can see that X comma topological space, and suppose Y be a point. Let Y be a point. Y is a singleton set. Maybe this is a notation, but We can also write it as some A. Okay. Then singleton set means the only possible topology is indiscrete topology. Empty comma that A. This is the only topology. Yeah. So with respect to this topology, this is always continuous. Okay. Continuous. Because what is the P image here? The only possibility is, so everything goes to the singleton set. Therefore, F inverse of this singleton thing, which is open here, open in Y, this is always X, the whole thing, which is always open. Open in X, or open in tau, whatever you say. So those are few examples, A, B. Another trivial example will be like, take, so let A contain in X and consider the subspace topology. Consider A tau A be the subspace topology. Consider this is the subspace topology arises from X comma tau. So if this is the case, then if we consider the inclusion map, F be the inclusion map. Inclusion means any point goes to the same thing. F of A equal to A. This is the map. It is just contained in that set, therefore there is always such a map. Then this is open, right? What will be F inverse of some open set U? So let U containing X is open. Then what will be F inverse U? It will be F inverse U means all such point A belongs to A such that FA belongs to U. But this is same as FA is identity which equal to A. So this is same as A belongs to A and also A belongs to U. So this is same as A intersection U or whatever U intersection A. But note that this is open in subspace topology by definition. The open set in subspace topology is given by intersecting with that subspace, that subset. Okay, so this is open in X and we are intersecting with A, therefore this will be open. Open in A with respect to the subspace topology. So those are few examples. Let us consider another example. Consider the identity map from X comma tau to X comma tau dash. And also assume tau dash is final. Okay, tau dash containing tau. So tau dash is finite topology. Now can you see that? So what is identity inverse? So let U be open in tau dash. Therefore U belongs to tau dash. Now what we need to prove? That identity inverse U is also open here. So is it true? Identity inverse of U. So identity sends everything to the same thing. Therefore identity inverse of U is U. But is it true that U is also open in tau? Can you say? No, because you can see that it may not possible that there can be something here which does not belongs to this tau, right? So this may not be open in x comma tau. That is, in topology tau, it may not be open. Therefore, the conclusion cannot be made. Right? So, this is continuous if there is equality. Otherwise, if this is strictly finite, if tau dash is strictly finite, then this is not continuous. Strictly finite means there is something here, some open set belongs to tau dash, which does not belong to tau. There is some, there is strictly more open set in tau dash. Right? So, this identity may not be continuous, may not, no, identity is not continuous if tau dash is strictly finite. What about the opposite side? So, if we take this map, now consider from tau dash to x comma tau. So, in this case, it is continuous, right? Because, exactly, because tau is smaller. Whatever open set we choose from tau, it is always open in tau dash. Maybe write in the opposite way, familiar one. So, whatever open in tau, that is always open in tau dash. So, this is continuous. CTS, I am denoting by shorthand. And we also know that composition of continuous function is continuous. You can check composition of continuous function, continuous map is continuous. So those are everything about continuity. I'm stopping at that point. Now let me start product topology. So what is product topology? Suppose we have two space, x and y be two space with topology some tau, or maybe, okay, x with equipped with topology tau and y is equipped with topology u. Now we want to create, so we already know about the Cartesian product, right? X cross y is the set which found by this kind of pair, x comma y, such that x belongs to x, y belongs to y. This is a set now. This is also called Cartesian product. So the thing, we want to create a new topological space from this given two topological space. So the set is, we already know about the set. The set structure is already known. Now can we topologize this set? So the answer is yes. How do we topologize? So the topology is given by this basis. Consider the basis if be some, let me denote it by, okay, here I should not write script u because I am also using, okay, u cross, let me denote it by tau dash, otherwise there will be some notational issue. So u cross v, those kind of open set where u is open in tau, that is U belongs to tau and P belongs to P is another open set in tau dash. Okay, so it will be of the form maybe this kind of UP, B capital UP. So those are open set in tau and tau dash. That is U belongs to tau and P belongs to tau dash. So this forms a basis, right? Okay. Uh, okay. So this is the topology. Topology generated by B, script B, is called product topology. The product topology on X plus 1. So let us compute an example. Okay. Here is a question. Let us compute the product topology in this case. So here two spaces are given, x1 and x2 with topology tau 1 tau 2. So this is the space x1 with topology tau 1 and x2 with topology tau. Now we need to find the product topology on x1 cross x2. So the first thing is we need to see the basis for this topology. Okay, basis for the product topology. So what will be the basis? Product topology. Script B, it will be of this form. So those are open set. We need to take product of those open sets. Okay. So empty cross empty is always empty, and empty cross anything will be empty by definition. One side is empty, so if you take product with empty, it is like 0 cross something is 0. Okay, so empty cross anything will give me empty, so I am writing empty set. Now let us see x1 cross those kind of thing. So x1 cross x2 will get this. Now x1 cross p and x1 cross pq. Another one is everything is done. Now there is another thing, a cross, right? A cross x2, this one, then a cross p and a cross pq. And another set, a cross pq. So the notation it will be like this. We can also write it in this way. I am not writing x1 cross x2. It will be all those pairs. There will be 2 cross 3. Therefore, 6 pairs. Right. So I am not writing x1 cross x2. Let us see x1 cross p. x1 cross p, it will be of this form, a comma p. Similarly, x1 has two elements a and b. We are crossing with p, so there will be 2 points a comma p and b comma q. Those are not interval, those are coordinate, that is tuples. Similarly, x1 cross pq, now it has more point ap bq, then sorry, this is actually p aq bq. Similarly, you can get a cross x2 which has 3 points. Similarly, you can write all those elements. Now, uh, can you see what is the topology on x1 cross x2? So how do you generate a topology if the basis is given? The product topology. So this is the basis for product topology. So how do you generate the topology? So the way is take union of basis element. Take all possible unions. Yes. So this is the way to generate product topology. So if we take empty with uh, if we take empty and take union with other element, that will be the bigger one, right? So uh, can we find some structure here? Then it will make the search easier. So let us see some kind of structure if it is there or not. That is, empty is always smaller, right? Empty is always smaller. Then okay, there are 2, 3 plus 4, 12 thing. Okay. Okay. Empty is always smaller now, and the last thing will be x1 cross x2. It is the largest possible thing. Now x1 cross p and x1 cross pq. So what are the relation? x1 cross p. This will contain in x1 cross pq, right? So I am writing the containment relation. Now a cross x2. A cross x2 is not contained in here, but a cross x2 is contains this and also contained in x1 cross x2. Now what about a cross p? A cross p is more smaller, so I am putting a cross p here, then a cross x2, and a cross pq uh, is in between, right? So there is something a cross pq here. So this is the structure. I am writing in poset structure. Those are actually containment relation. So we need to take union of all possible unions. So there are 1, 2, 3, 4, 5, 6, 7. So I have written all those things. No, there is one element I have not written. x1 cross p, x1 cross pq, a cross x2. Okay, a cross x2 is not written. So a cross x2 will be under. Okay. So note that if you take union of those two things, it will be the larger one, right? Can you see all those elements? If you take union of the larger union in any chain, so if we take union in this direction, it will be always the larger one. Similarly, union of those three things will give the greatest one. So we will not get anything new. So to produce something, some new element, we need to take union of those disjoint thing. Okay, union of these two or union of this with this, those kind of union, right? So the topology will be given by take empty and those kind of thing a cross p. There will be some bracket I have already missed. A cross p. Uh, sorry. Yes, a cross p. Those kind of bracket will be there. A cross p, then a cross pq, then a cross x2 and x1 cross p, x1 cross pq, x1 cross x2. Now we need to take all such possible unions. For example, we can take union of union. So there are also more relation. For example, a cross p, that will be contained in x1 cross p, right? You can see that uh, a cross p means this singleton element. A cross p, it will look like this set. So this is contained in this x1 cross p. So there are more relation. So this contained in there. Similarly, this will also contain here, and this also contain here. So those are relations. Will there any other relations? Yes, this is also content here. Okay, so this is just composition of those two containment. So now we need to take every possible unions. So what are the non-trivial unions? Can you see some non-trivial unions here? For example, this and this, there is no relation between those two things, right? Those two are in diagonal position, so there are no relation because this is not contained here and vice versa. So this kind of union should be there. So we need to take x1 cross p union a cross pq. Okay. So there are other choices we need to see. Uh, sorry, this is not true. Okay. This diagonal, this direction is not true. Similarly, we need to take union of this with this, right? So a cross x2 union x1 cross pq. But we also need to see that those kind of unions should not be there, which is not, uh, which will be not true. But we also need to see those kind of thing. So probably all those are all open sets, but you also you need to check that there is no other choices. Those two pair is chosen, those two pair is chosen, and is there any other combination? For example, this pair and this pair. Okay, we also need to take those two pairs. So we need to write all those possible combinations, and that will give me the product topology. there will be other elements. So that is how we will get the product topology. So let me write in more general manner. So now there are collection of topological spaces xi comma tau I. Okay, I belongs to I. Those are given spaces. So again we can take the Cartesian product of this space. It is I can be some infinite set. So product of xi, it will look like some kind of thing, x1 cross x2 x3, and it will goes to infinity. Okay, those kind of product, but I can be also some real number, right? Then we cannot write in this manner, in a sequence like this. So how do we define a topology on this set? So one way will be like this. So want to topologize this product. Cartesian product is given. So we want to topologize this product. So there are two ways. Okay. One way will be like this. So let me create a function. This is Cartesian product. Therefore, we can make projection map pi I or maybe pi j, which projects on jth component. So it will project everything to the jth component. Okay. So if we think this as a sequence, something like this, x1, x2, x3, though it may not be always like this, but if we consider those kind of things, then for example, if we take projection on the first component, it will send everything to the first entry. Similarly, projection on the second component, it will send everything to the second entry. Okay, so those are projection map. So we can form a basis, sub basis, like this. Pi I inverse of some ui. Okay, where I belongs to I and U is open in xi. That is U belongs to tau I. UI. So that will give me a subbasis because what is the definition of subbasis? Subbasis means it partition this product. So you can check that if you take union of all those things, that will be the product. Okay, that's why it is a subbasis. So let me write in a simple manner, otherwise it will be something difficult. Example, consider this kind of product of xi I equal to 1 to infinity. Okay, then the subbasis will be like this. For example, what will be pi 1 inverse of some u1? It will u1 and everything is same, that is same set, x2 cross x3 dot dot. Because whatever, that is, if we take the projection pi 1, then it will send me to u1 because those terms, the projection does not depend on those terms. So everything will be there in pi 1 inverse, right? So subbasis will look like this kind of set, some u1 and everything is same. Similarly, pi 2 inverse of some u2, where u2 is open in, so u1 belongs to tau 1, u1 is open in x1. Similarly, this is some x1 cross u2, and everything is x3, x4, those are fixed. Those kind of thing. And it will continue. u2 belongs to tau. So those are actually, those forms a subbasis, and the topology generated by this subbasis, this is called product topology. Okay. So how do you generate a topology? First, from this subbasis, we can create a basis. This is an example. So how do we create a basis? We need to take finite
intersection.
Exactly. So the finite intersection, it will, so this subbasis is sometimes denoted by this kind of script S, and basis is denoted by this script B. So what will be script B? It will look like product of some ui, I belongs to I, where ui is open in xi, that is ui belongs to tau. Okay. And there is another thing, ui equal to xi for all but finitely many I. For example, if you intersect those two things, what will you get? If you intersect those two things, then this intersection, yes, this intersection will give me u1 cross u2, and everything is fixed, right? x3, x4, so on. So if we take finite intersection, then it is clear. Only few component will be independent. Only few component will be some u1, u2, some open set. Other than those component, everything will be some x3, x4, those kind of thing. So I have written that thing, that is ui is xi for almost everything except some finitely many coordinate. Everything is that whole xi. Okay. So this is how we can topologize the product xi. So here the yeah.
So how are you getting pi 1 inverse u1 is equal to u1 cross x2 cross x3?
No, I am not saying that. Oh, sorry. Here, why are you getting this?
Yes, sir.
Okay. So let me the definition. Pi 1 inverse of u1. Okay. This means something. So it will be some kind of point, some xi. I belongs to I, such that by definition pi 1 of this xi, this is the
Belongs to u1.
yes, pi I of this sequence. I am writing in this notation, this equal to
Belongs to u1.
this belongs to u1. u1,
Yes, sir.
right? Then what is the meaning of this pi? What is the pi 1 of this sequence? This is the sequence. What is pi 1 of this?
Sir, it can be anything in u1.
No, by definition pi 1 means everything goes to, so if we write in a sequence, for example x1, x2, then
Okay, sir. It goes to x1.
yes, pi 1 sends everything to x1. Okay. Similarly, in the better notation is
Yes,
like
sir.
this:
Yes, sir.
xi, I belongs to I. So if we evaluate at ith point,
Pi j.
yes,
It goes.
at sorry jth point, it will be x.
Yes, sir. Yes.
So that's why I will get. So here it is sequenced. So the first coordinate will be x1. That is the thing I am writing, that only the first component belongs to u1 and everything other component can be anything. Okay,
Yes,
so
sir.
that's why it is u1 cross x2 cross x3 like this.
So it will be subset of U1 cross X2 cross X3.
It's not subset, it is exactly this. That is, you send those kind of thing, you will get x1.
We have to prove other side, na sir?
Yes, if you take anything, if you take a point uh, which does not belongs to this set, that cannot maps to x1, right? Take any point from the complement of this set. If you take the projection, complement of this set means the first point must not belongs to u1, right? And if the first point does not belongs to u1, then the projection cannot be x1. That's why this is same as this, not the subset of this. Is it clear?
Yes, sir.
Okay, you can do this exercise. This is some set theoretical exercise, you can check. So the topology generated by this script B or by script A. So topology generated by subbasis means first we form a basis and then from this basis we'll take arbitrary union. Okay. So topology generated by this basis script B is called the product topology on this product. I belongs to I. Okay. Now there is another way to topologize. This is one way. First, and the second one will be like this. So it is similar to the first one. So now take the product ui. I belongs to I, but ui uh, is open in xi. That is ui belongs to tau I. Now we are not restricting anything. So there is no other condition. That is, except for some finitely many ui's, all are xi. This condition is removed. There is no condition. Those are independent open set. Some kind of u1, u2, like this. There is no restriction that all those other things will be the whole space. There is no such condition. So this forms a basis. You can check that intersection of those kind of set is also open. Because of this property that if you take A cross B and if you take intersection with C cross D, again the set theoretical property, this is A intersection C cross B intersection D. Okay, you can check that this forms a basis. That intersection of any two thing will be open itself. So more than a basis. The condition asks that there should be some open set which contain in the intersection for any point in the intersection. But it says that intersection of those kind of thing will be, again, it will look like open cross open. So this is true for any arbitrary product, not only for those kind of product of two things. So this form a basis, and the topology. So let me denote this by B dash topology. So this looks like some box, right? For example, uh, this is U1, some open set. This is U2. Then the product, geometrically the product will look like this, a box. Similarly, if we take another U3 component, then it will be some kind of box like this, right? It is like R cross R cross R. It becomes R3. R cross R, it becomes the plane R2. So those kind of, it the basis takes this kind of forms. That's why this is called box topology. Okay, the topology generated by B dash is called the box topology on this product Xi. So this is how we can define box topology and product topology. But the important topology is this topology. This product topology is more important. Okay, we'll see why that is more important. We'll see later. But this is not very useful. Though this seems more natural because we are taking product of, that is, there is no relation. We are just taking product of on each component. Take some open set and we take our product of those open set. But this topology is not that much useful. Okay. So you can check some properties. We can we'll, discuss later. So first one, note that box topology is finer than finer than product topology. Right? You can see that box topology on product Xi, because what are open set in this product topology? This kind of thing, right? This is this is open in product topology, but this open set is also open in B dash. There are some relation, but there is no relation. So everything from this B also belongs to this B dash. B containing B dash, right? Since B containing B dash, therefore the topology corresponding to this tau dash, it is also contain tau. That's why the box topology is finer than product topology. And moreover, just note that if I is a finite set, this I is a finite set, then this condition, is it any meaningful condition? Then you can avoid this condition, because you are taking, yes, exactly, we don't require this condition because everything is finite. So except finitely many I, ui is same as xi, that condition is means it is already absorbed in this definition. If you do not write, then there is no issue for finitely many product. For example, some kind of, if we consider the product of x1 cross x2 dot xn, for those kind of case, these p and these p dash, those two are same. Those two are same for finitely many product. Okay. So here another remark: this equality holds. Those two topology are same if we consider finite product. Okay. Otherwise, we can't decide. We need to check that if that is finer or not. So those are some interesting example to create topological space. So first example was the natural one, subspace topology. We just restrict those open set in that subspace. Take intersection with that subset. So that gives subspace topology. For product topology, what are we doing? We are generating the topology by this kind of open set. Sorry, not this. This kind of product of ui, where ui is same as xi for all but finitely many I. So uh, I need some times to define quotient topology. So let us solve few exercise before that. Here the usual topology tau on R, this is given, and that is R is equipped with the usual topology tau. Now we need to consider the relative topology. This is R, and the subspace A is given by this closed interval 0 to 8. Now the question is, this closed open interval, this is open in relative topology on A. So relative topology means the corresponding subspace topology. Okay. So is this set open in the subspace topology? We are considering this set 0 to some 5 and 7 to 8. Is it open in relative topology? What is your answer? No. Why not? Can you see that 0 to 5, is it open in the subspace topology? So is
Taking intersections.
exactly. So 0 to 5, that can be written as just extend on the left. Then we may take minus 1 comma 5 and intersect with A. Right? This is actually open in R. Some open set intersection with A. Exactly. So therefore, this is open in the subspace A. Right? Now can you see that 7 comma 8, this is also open in A? Yes, because 7 comma 8 can be written as 7 comma 8 intersection A. It is already contained in. So those two are open in A, right? Therefore, the union of two open set is also open in A. So this option is correct. Okay. Now what about the second one? Not open in. So first one is true. Therefore, the second one is false. Now what about option C? Is it open in the usual topology? Is it open? Not true. Why not true? Because we can see that 0 has no neighborhood. Whatever neighborhood we take, it will be some minus epsilon comma epsilon. This open interval cannot be entirely contained in A. Right? So this cannot be open. Is it closed in the usual topology? Yes, you can also say. In terms of basis, yes. Is it closed in usual topology on R? No, exactly. Why? Again, why this is not closed? because some limit points um, are not there. For example, 5 is not there. 5, though 5 is a limit point, it does not belongs to the set A. Closed means it contains all the limit points. Okay. Yes, you can also think in this way that complement is not open. Exactly. Great. So let us see what is the complement. A complement is same as minus infinity comma 0 union 5 comma 7 union 8 comma infinity. So this joint union of some sets, this is open, there is no issue, right? Because open in sorry, we need to check the complement of this set. Let me denote it by some. Okay, it is complementing R, that is okay, but this is some set S, then we need to check the complement. So this is actually R minus S, but we need to see the complement in A, that is we need to take the intersection, right? So that is on R, on 0 to, on the intersection, the complement is only this set union 8, 5 comma 7 union uh, this 8 is also there. So we are taking this complement A minus S. Okay, so we can see that this is not open in A. Exactly, because of the issue 8. 8 cannot, we can see there is no neighborhood which entirely contain in the set S. Okay, whatever neighborhood you choose any neighborhood of 8, it will look like 8 minus some epsilon 1, 8 plus some epsilon 2, this kind of open interval which cannot be entirely contained in this set. This set. So let me write another thing. The neighborhood eight minus epsilon 1 comma 8 intersection A cannot be. So this is actually intersection with A, means it is 8 minus epsilon 1 comma 8. This is the neighborhood. Okay, cannot be contained in S. So that's why this is not open. Therefore, A minus S is not open. S is not closed. Is it understood? So to see if something is open or not, we need to check in terms of basis. We take a basis neighborhood of this 8, but whatever basis neighborhood we take, that does not entirely lies on this S, lies in S. So
Sir,
yes,
sir, we need to find neighborhood in terms of subspace, no, sir?
Yes, that's why I am taking this kind of thing. This intersection with A, which is 8 minus epsilon 1, comma, closed 8. Is it understood? So this is how the neighborhood will look like in this. Okay, sorry. So I am checking a different question. This is closed on R. So let me modify this question. This is closed. So if this is the question, then we have seen that this is not closed in the relative topology. So again, this is false. And closed in the usual topology, this is easy to check, right? The similar kind of check, but it is more easier. So this is also false. Is it clear?
Sir,
Yes. Go ahead.
sir, you have taken some particular type of the neighborhood.
Yes. I
You
have
should
taken
have
because
proved that there does not exist any neighborhood. It does not
yes,
prove that there does not exist any neighborhood.
exactly. Why I am choosing, because it is enough to choose basis only. I am choosing a basis element, basis of the subspace. So this kind of element a comma b, this forms a basis for real number, right?
Yes, sir.
Basis for usual topology. That's why I am varying this epsilon 1 and epsilon 2. And if we take intersection with A, that will form a basis for the subspace topology.
Okay, sir.
So instead of checking with any arbitrary neighborhood, it is enough to check with basis element. Because we know that any open set will contains a basis element by definition of basis. Not definition, but by definition of topology generated by a basis. An open set, take a point in a open set, there always exists some basis element which contains that point and contain in the open set.
Yes, sir.
That's why it is enough to check with those kind of basis element. So this cannot be contained in S for all epsilon 1 epsilon 2 positive real number. Okay.
Okay, sir. You are proving that for any element belongs to this set, there does not exist any basis element such that that element belongs to the that set, that basis element and is subset of the set.
Yes. So I am choosing a basis element which contains 8. So it will look like this. Any typical basis element. This intersection with A,
Yes, sir. Yes, sir.
and I am proving that this cannot be entirely contained in S because
Yes, sir.
8 cannot be there.
Yes, sir.
You
Yes,
can see that 8 does not belong to this S. This is the reason.
yes, sir.
Okay, great. So quotient I have not defined. I will define later. So um, this exercise. Okay, again. First, we need to find product topology, and then we can find. But that will be time consuming, so I am not solving this right now. Let me solve few questions. So okay. So product of Hausdorff space is Hausdorff with respect to product topology. Is it true? Suppose x1 and x2 are two Hausdorff space. Will the product also be a Hausdorff space?
Yes, sir.
Okay. let us see if it is true or not. So let 2 point x1 comma x2 belongs to this, and another point y1 comma y2 also belongs to this. Okay, such that those two are different. x1 comma x2 is not equal to y1 comma y2. So what is the meaning that two things are different, two tuples are different? This means either x1 not equal to x2, sorry, either the first component will be different or the second component will be different, right? So now, yes, since x1 is Hausdorff, that will imply that first two component different, that will means, so without loss of generality, let us assume the first component are different. Okay, without loss of generality, let x1 not equal to y1. Then since x1 is Hausdorff, there exists some u1 contained in x1 and v1 contained in x2, maybe u and v, those are two open set which separates this x1 y1. Okay, those are two open sets such that x belongs to u, y belongs to v, and u intersection v is empty. So this is true, right? By definition of Hausdorff space. So if this is true, now consider the product. So u cross x2, this is open in this topological space. Sorry, both are actually open set in x1. Sorry, x1, and we are considering x1 and y1. Therefore, there are open set which separates those 2 points, x1 and y1. Okay.
Yes, sir. This is correct, sir.
Okay. Now we can consider this product u cross x2. Okay.
And V cross X2.
Yes, and v cross x2. Note that this x1 comma x2, this belongs to this thing because
Yes,
x1
sir.
belongs to u, and similarly y1 y2 belongs to this, and moreover the intersection is empty. Because of the fact that intersect commutes with product, that is, this is same as u intersection v cross x2 intersection x2, which is x2 itself. Okay, so product of from this fact, and also note that this is open in the product topology by definition, that one component is the open set and other are some x2 or something like this, so that must be open in the product topology. Okay, only finitely many components are some arbitrary open set, other than, so it is only finite case, we are considering finite case, so there is no issue. So product of two open set, that will be open in product topology. This is open in product topology. So which is empty, empty cross x2, which is empty. Therefore, we are done, right? We are able to find two open set which separating those 2 points. Is it clear?
Yes, sir.
So product of Hausdorff spaces is Hausdorff. Good. Now what about product product of Hausdorff spaces? So the first one is with respect to product topology. Now what about with respect to box topology? So again, if we give box topology, if we consider box topology, then will those two things be open in box topology? Will those be open in box topology?
Yes, sir.
Yes, because in box topology there is no restriction. Box topology means product of open set. It is open and this is also open. X2 is also open in X2. So product of open set. Yes.
Sir, if tau 1 is coarser than tau 2 and tau 1 is Hausdorff, then tau 2 is also.
You are saying that tau 1 is coarser than tau 2.
Yes.
So if tau 1 is Hausdorff, then tau 2 will be also Hausdorff.
Yes. This
So
need not be true.
yes, because tau 2 has more open set.
Yes, sir.
So using the first previous open set, whatever open set we are choosing in tau 1, we can separate it by the same open set, because the same open set is also belongs to tau 2. Okay, so using that you can also say, because product topology, we already know that product topology, this is coarser than box topology. So this first will imply the second. So
Second will imply first.
uh,
Second will imply first.
no, box topology is finer.
Yes, sir.
So if we can separate in product space, then we can also separate in the box topology, because box topology has more open set. Okay,
Yes, sir.
so
This statement is true, no, sir? If
yes,
coarser topology is Hausdorff, then the final one
finer one
will
will be Hausdorff too.
yes, sir.
So that is the thing. So yes, so option A, product is Hausdorff, and using the fact, you can either use the fact or directly also you can prove finer topology.
Sir, you have proved for finite product.
Yes, I have proved for finite product, the same proof goes for arbitrary. So instead of x1 x2, if you consider those kind of sequence, then that is also correct, right?
Yes,
There
sir.
will
Yes,
be some index for which xi not equal to yi, and we will consider that index.
yes, sir.
Okay, so using that index, we will choose at ith point we take ui, and other than that point we choose those kind of thing, some x1 cross x2, xi minus 1 and xi plus 1, like this. Is it clear? For infinitely many things, how can we deal? For countably many things, the same way we can deal, and the same will be true for infinite, means even the index is uncountable, there will be some I for which xi not equal to yi. Use this fact, we can create, by definition we have this kind of thing, and just take that product. Except ith component, everything is fixed. Everything is some xi. except this fixed component, everything is some x1 x2 like this. So this is true for also the arbitrary product, not only product of finitely many things, but this is true for arbitrary product as well. Now what about subspace of a Hausdorff space? Is it Hausdorff? Tau 1, tau 2, and this is Hausdorff. Tau 1 is Hausdorff, imply tau 2 Hausdorff. So using this fact, we claim that B is true. That is, box topology is Hausdorff. Now what about subspace? So A is a subset of X. It is given that tau on X, the topology this X comma tau, this is Hausdorff. So what about the relative topology on
This
A?
is true, I think, sir.
Okay, let us see. So we need to see topology on A is Hausdorff, relative topology. So choose 2 point P comma Q belongs to A, two distinct point P not equal to Q. Okay. Then P comma Q belongs to A, that also means P comma Q belongs to X. And X is Hausdorff, so we can separate it by two open set. There exist open sets in X, UP comma UQ containing P comma Q respectively, such that UP intersection UQ is empty. Right? Since this is empty, then restrict it over A. So if we again intersect with another thing, that will be again empty, right? Because intersection will give me something smaller. So that is same as UP intersection A and UQ intersection A. Is it clear that this is open in A? By definition of relative topology or subspace topology, this is open in A. Exactly. Open in. And this also contains P comma Q, because P also belongs to A. P belongs to A and P also belongs to U. Therefore, subspace of Hausdorff is Hausdorff. So Hausdorff property is preserved by product. It is also preserved by subspace. Now there is another question: will it be preserved under quotient topology? So we'll see later. So 1, 2, 3 is correct. We'll see the last property. So again, there are some questions which says, first one says that, okay, let me solve it later. There is another nicer question. So before that, let us see this question. So first one says this kind of thing: minus 1 by n comma 1 by n. We are taking the product from 1 to k. That is, explicitly it will be like this: minus 1 comma 1, then minus half comma half. For n equal to 3, we will get 1/3 comma 1/3, this kind of thing, and it will goes to 1 by k to 1 by k. Now will it be open in product topology? Is it open in product topology? So again, we are considering R with usual topology. If no information is given on R, then we will always assume R is equipped with usual topology. Okay. So what about the first one? That is it open in product topology?
Yes.
Yes, exactly. Because for finitely many product, Rk means it is this kind of thing, product of R k many times. So this is open in product topology. Why? Because this is also a basis element. You can see that basis element is given by product of open set. So those are open in R. Therefore, this is open in Rk. Okay. Now the question, is it open in box topology?
Yes, sir.
So
For finite case, both are same.
yes, for finite product, box and product topology are same. Now what about C? Is C open in product topology? So for C, it will goes to infinity. This step will not end. So now what can you say? Will it be open in Rn with respect to product topology?
Sir, I think no.
Why no?
Why no?
Why this is not the case? Why this cannot be open in product topology? So how do you check if something is open or not in terms of basis?
Sir, we can write as union of basis elements. Or you can take any element belongs to this
Yes,
set
we need to
and
check
find some basis element such that
exactly.
the basis is contained in that.
So we want to prove
So this
that
is
this
not
is
true, sir. This is
yes.
not open
So
because
how
there are, sir, finitely many sir, intervals and at infinitely many times are, sir. So
yes,
it cannot be contained in this.
your guess is correct, but can you see that there exists some point for which there is no such neighborhood
Sir,
which
you can
contain
take zero, zero.
yes. Take this 0 point 0 0 0, everything is 0, right? This belongs to this set.
Yes, sir.
0 belongs to this kind of thing. Every open set contains this 0.
Yes, sir.
But what will be a basis neighborhood of 0?
There are finitely many spaces, some intervals, and at infinitely many spaces are
Yes.
product.
It will be given by some open
U1
set,
cross U2, sir, up to UN
product of
cross R
ui.
cross R.
So in the first case, I have said ui is so ui is R, where ui is the whole set for all but finitely many I.
Yes, sir.
Okay. So a basis neighborhood of 0 will look like this. So can it be contained in that set? So suppose this is the set S. So can this product contain in this S?
No,
This is not possible because R does not belongs to minus 1 by k comma 1 by k, for means it is not possible.
yes,
This is not
Sir,
possible for all.
sir, is there any element uh, different from 000 in this set?
Any element from 0 0 different from 0. Again, the same thing you can say.
No, sir.
Instead of 0, you can choose any other element also.
Can
But
you?
the problem is if you choose anything, so eventually this should be 0. Otherwise, you cannot argue in this way.
Can
Yes,
you do any other element other than 000?
yes, you can also choose any other element other than 0. There is no issue. Yes.
Sir, what kind of element?
What kind of element?
Yes, sir. Can you provide some element other than 000?
Yes, I can definitely provide. It will be like something like this. So those are interval. It is product of minus 1 by k. So take this kind of thing, right? Um, Something like 1 by 2k. K belongs to n. So that belongs to this product. Can you see? This belongs to the product. Something in between. So there is a space from minus 1 by k to 1 by k. There is a space. So you can choose anything. For example, 1 by 2k. I have chosen 1 by 2k. So
Yes,
this will
sir.
vary. Okay, that is enough. So from here it is clear that this is not open in the product topology. Now what about with respect to box topology?
So it is open.
Yes, in box topology this is open because in box topology there is no restriction. In box topology, in the box topology there is no such restriction. No such restriction. Therefore, S is open. Great. Now let us see why uh, we are. I have already said that product topology is better topology than box topology. So this example will uh, give us the reason why product is better than box. So F is a map from R to Rn, and it is given by component wise. So everything T, F of T, each component it is identically maps. It maps identically. Okay, this is the map. Now we need to see that if this map is continuous in product topology or not. Okay, so what is your guess? Will it be continuous in product topology? So first, let us uh, yes. So let us see what will happen if we consider box topology. Okay. So we see that continuity. What is the meaning of continuity? F inverse of open set is open. We need to check if this is true or not. We need to check this property. So what about the first one and what about the second one? Will it be continuous with respect to box topology?
Sir, in first one it is continuous. In second one it is not.
Okay, let us see why this is the case. So consider the open set minus 1 by n comma 1 by n. So this is open in box topology. In box topology. So first I am solving the second problem. Okay, so this is open in box topology. Now what? So this is U. So what is F inverse U?
Singleton zero.
Yes. Why? So F inverse U, it will look like this kind of sequence: x1, x2, dot dot. This belongs to R. Sorry, F inverse U domain
X
is R.
belongs to R.
Yes, it is x belongs to R, such that
F of X belongs to U.
f of x belongs to U. So this is product. Um, so f of x is that is if and only if this x comma x dot dot this belongs to this product n equal to 1 to infinity, right?
Yes,
So
sir.
that is same as saying x belongs to minus 1 by n comma 1 by n for all n, right? So can you see what is the element which belongs to all such intervals?
Zero.
Exactly, because this interval is shrinking, so only 0 will survive. 0 belongs to all those minus 1 by n to 1 by n. So this thing is 0. Now can you see that the question is
This is
0
not
open
open
in R?
in usual topology. No, not
Yeah.
open.
So 0 is not open in R. So we have started with an open set, and we see that inverse f inverse of that open set is not open, right? Therefore f is not continuous with respect to box topology. Okay, but the interesting thing is that it will be continuous with respect to product topology, right? So how can we check? We can check the continuity property in terms of basis. Okay, so take a basis. So basis will look like some product of ui or un, maybe un. So this is a basis element of this product topology, that is r to the power n. R to the power n means I am taking natural, that is countable many product. Okay, countable product this is. So r cross r it will goes on. So if we consider a basis element, what is the meaning of this? This means un equal to r for all but finitely many n. So except some finite number of n's, if all those un's are r. Now what about f inverse of un? F inverse of this product. So I have chosen a basis element. We need to see that. So we can prove the continuity in terms of basis. F inverse of basis element, we need to see that if it is open or not. Okay, that is enough. So can you see that this is open? So an exercise that f inverse of this product, that is nothing but this un equal to 1 to infinity. Now, so I have assumed un is r for all but finitely many n's. So let us also assume those finitely many n are n1, n2, and up to nk. For those values, un are some independent open set, except that everything is r. Then can you see that this is same as those un1 intersection this? Can you see this is the case? Because everything other than
Yes,
those
sir.
n, yes, everything other than n1 up to nk are real number.
Yes, sir.
So if we take intersection, we always take the smaller thing. It will be
Sir,
consumed. Yes, r is consumed
sir,
by intersection.
F inverse of product un is equal to intersection of un. It is because, sir, by the definition, sir,
Yes,
of
exactly. Because x belongs to the product of
X will belong to all ui, so X
yes,
belongs to intersection.
yes, this kind of reason. The same reason. X
Yes,
belongs to
sir.
all those ui, all those un for all n belongs to n, which is same as saying x belongs to this intersection.
Yes.
Exactly. Great. So now can you see that this is open or not?
Yes, sir. This is open, sir. Finite
Why?
intersection. Finite
Exactly.
intersection of open sets.
Finite intersection of open set.
Intervals, actually.
Yes. Therefore, f inverse of this thing is open. Therefore, this is open. So f inverse, we have just proved that f inverse of any basis element is open. And I already said this condition is enough. Why? Because any open set that can be written as union of basis element, right? So if you can prove this is open for basis element, then f inverse of open means this is same as union of f inverse basis element, which is taking union of basis element, union of those open set, which will be open. So it is
Yes,
enough
sir.
to consider on the basis element.
Yes, sir.
So we are done. We have proved that f inverse of any open set is open. Therefore, this is true. Okay. Therefore, f is continuous in product topology. So this is the reason why product topology is important. Product topology means, so we are considering topological spaces A and xi. I belongs to I, right? Then if maps A to product of xi, I belongs to I. Reason, this is
Sir, A is any set.
A is, those are topological spaces. Topological spaces. Okay, so we can define this by component wise. So f of A, it will look like some f1a up to f2a. Those are maps. Okay, so it is not this kind of sequence because may not be countable, but it will be fia, I belongs to I. This kind of sequence notation. So f maps A to product of xi. This is continuous if and only if each fi are continuous. If and only if each fi are continuous. So the same proof will work. whatever the technique I have just written, the same proof actually works in more general case. That is, if all those components are continuous, it is given, then you can prove that this is continuous. And this side is more easier. That is, if this product map is continuous, then fi is all those fi continuous. This is easier because take the projection map pi I, and you can prove that a to xi. So you can prove that pi I map projection maps are also continuous. This is very easy. You can just prove. Okay. That is why we are considering product topology. Product behaves well with respect to continuous function. That is, the interesting thing is that if we consider some kind of map a to x1, a to x2, a to x3, if we consider those kind of map, it is same as considering, this is equivalent to considering a map from a to x1 cross x2 up to there. Okay, that's why product is important. That is, all those information will be carried by this single map.
Yes, sir.
That's why product is more interesting. Product is more categorical. That is actually a categorical notion, and product behaves well, not box topology. So I can't solve any problem from quotient topology. So let me say about this fact. So this is also true. If we take interior, product behaves with respect to interior. This is true for finite product only. You can prove, very easy proof. Okay, but if you consider infinitely many things, so all those product notation, here we are considering product topology, but this false. Can you see that why this is false? Product of interior is not. First, if we consider, so interior of product is not product of interior. Can you see why this is false?
Well, if we take R as the usual topology
Yes.
and take set of real numbers,
Okay.
but then R interior, sir, will be, sir, R cross R cross R, but it is not open in some product topology.
Uh, what are you saying? What is the claim? So I have already provided the answer actually. So for B, this is exercise. For B, you can see that if we consider
Sir,
this,
T,
yes, xi equal to minus 1 by n comma 1 by n as a subspace of R, then what is the interior of this xi?
that's it itself.
Interior of xi is xi itself. But for product of xi, so if we take this interior product of xi interior, this becomes this kind of thing, right?
Yes, sir.
Can this be same as this? Is it possible?
No, sir.
Why? Because interior is always open set.
Sir, 0 belongs to this, but there does not exist any basis element in product such that the basis is contained in this.
Yes. In this way you can argue, but there is more easier way, because you can see that interior is always an open set, but this cannot be open in product topology, right? This is open set, interior is always open, but this cannot be open in product topology. So product, this I am considering this product Rn. Okay, so those are actually not space, those are subspace of some bigger thing, because when we consider interior means everything are considered as a subspace of some bigger space. So here y is our R. Okay, so we have seen that this, if we take this can product, because this is open but this is not open in Rn with product topology, with respect to product topology. Is it clear? So this is not possible. This is open, this cannot be open. So this equality is not possible. And option C is correct. You can read the proof from Munkres. It is already given that product behaves well with respect to closure. So first you take closure and take product. That is same as first you apply closure. That is closure of the product. Closure commutes with product. And the same thing goes for box topology also. Instead of box product topology, if we consider box topology, this statement remains true. And moreover, this becomes true. That is the interesting thing. So you should prove those facts.
Yes,
So
sir.
today I have only discussed product topology. So we'll discuss quotient topology in the next lecture, because it will take some times, at least 30 minutes.
Yes, sir. So we can wait if you want to explain.
Mm,
Yes,
I it will take 30 minutes at least, and also there are lots of questions. So
Sir, only the definition of the quotient topology,
okay, so
then
let
you
me
can.
motivate. This will be the better thing to do. Let me motivate about this quotient topology. Okay. So what is quotient topology? Okay. Suppose I have given you the interval I, close 0, 1. Okay. Just think it as a thread, as a small thread. And now I said you to identify this 0 and 1. Okay. Identify this 0 and 1. Identify means it is same as saying glue this 0 and 1. Identify or glue or whatever you say. Then can you see what this becomes
Sir, can you explain what
Closed loop.
exactly. It will become something like this. There will be something here and something like this, right? Let me give another example. So consider this square, a rectangular paper. Consider this paper, okay? And now I asked you to glue those two edges. Glue those two edges point by point. Glue these two edges. Identify means just glue. Means these 2 points are, think those 2 points as the same point.
Like some cylindrical shape.
Yes. Identifying means think those 2 points as the same point. For example, this and this are same. This and this are same. Those this point and this point by point. I am identifying those 2 points as the same point. Is it understood? So okay, great. So if we identify, then that becomes something like this. So there is something here and it will be something like this. So is it clear that this becomes some cylindrical shape?
I think geometrically I understand.
Yes,
Can you
geometrical.
explain how to think of it?
Yes, I will say how to think more mathematically, but let us start with this example. Otherwise, it will be an abstract definition. That's why. So let me identify. So two sides are identified point by point. Now let us identify those two edges. So now identify this and these two circles. Identify those two circles
As same.
point by point.
It will
Now
become a circle.
this is a cylinder, okay, hollow cylinder. Now you are identifying those circles. So deformation is allowed. You can just deform. It is hard to deform a something like sheet of paper, but you can think it as a rubber. Okay, this is a cylinder made by rubber. So you can just
Twist it.
yes stretch. You can stretch or deform those kind of shape. So now can you see if we identify what will be the shape?
Sir, sir, crushing is also allowed.
Yes, means you can only stretch. That is some there is some interval 0 1. Then you can stretch it to something like this. Those kind of step are allowed. So let us draw the picture. Can you see that this picture will be like this? Can you see? Those are blue. It becomes a torus or donut shape, whatever you say. This is a hollow cylinder. Is it clear that this shape becomes a torus?
Yes, sir.
Okay, great. There is also another way to identify. Again, we can identify those two sides, but now the rule is identify this edge with this edge, but in a opposite manner. That is, this point that will be identified to this, and similarly this point will be identified to this. That is in a opposite. That is this edge.
By twisting.
Yes, this edge will be identified with this edge, but in a opposite direction. Now, can you guess what will be the shape?
Mobius.
Exactly. It will become some kind of Mobius strip. So, something like this. Maybe it is hard to draw. Okay. It will become a Mobius strip. Sorry, I have forgotten how to draw. Okay, whatever. It will become Mobius strip. So this is the motivation. Now you you started with a topological space. Suppose X is given. Topological space. Okay, and you are identifying some points of this topological space. So the information is this. Another information is equivalence relation on X is given. Okay, this is an equivalence relation. What is the meaning of equivalence relation? A is related to A.
Transitive.
Yes. So there is relation like this. Those kind of pair will be there. A comma A. That will belongs to the relation, and A related to B will imply B related to A. That is saying that is AB belongs to the relation, imply BA belongs to the relation. And similarly is transitivity. So equivalence relation is nothing but partitioning the set X. So X is partitioned into some relation. Partition X. Okay. For example, consider this X. Example X equal to this 3 point ABC. So you can partition this X as this A and partition into another part as BC. So you can define the equivalence relation as A related to A. Okay. If something belongs to that set, those two are related. For example, B and C are related. A is related with A. Let me add few more elements. D, E, F. Suppose this is partition into another part. D, E, F. So two element X comma Y, those are related if and only if X, Y belongs to the same partition. Same partition. Then this is an equivalence relation, right? So every equivalence relation arises in this way. Okay. So suppose the topological space X is given and there is another equivalence relation. Now you can identify those points as a as one point. For example, you can think BC as a single point, DEF as a single point, right? So as a set, this will be like this. You already know about coset, right? G mod H, group coset.
Yes, sir.
Yes. Then great. Then everything will be some kind of coset. So think A as a single element. Think BC as a single element. So I am creating a new set using that X and equivalence relation and treat DEF as a single element. You already know that you can also denote this by some kind of B bar, some kind of any element representing that set. In group theory, you already know about this. So from a given set and a given equivalence relation, we can always create another set. The information can be written in terms of a set. But the question, can we create a topological space? Suppose X is a topological space. Now can we give a topology on this X modulo that relation? Can we provide?
Sorry, sir.
So given a set with an equivalence relation, we can create a new set using that relation.
Yes, sir.
Now see that X is a topological space. The question is, can we create another topological space using that relation? That is, can we topologize this X modulo the relation? Can we topologize this? This is the question.
Sir, we can use it as sub basis.
Okay, so here it is slightly different. Let me say how this comes.
Sir, if it can be formed as a subspace topology, mm, but
Yes,
we can't do that for every set, right? If the topology contains these elements only, then we can make a subspace topology out of it.
okay. Um, yes, you can think in that direction, but that direction will not use this kind of equivalence relation, right? I want to use that relation also. Okay, so there is a way. Let me again draw that picture. So 0 and 1, those 2 points are identified, and then 0 identified with 1. So I am taking the topological space I, and I am identifying by the relation only 0 and 1 are identified. All those other points are, that is 0 and 1 is the set. So X mod, this will look like this 0 1, and all other points are singleton set. Okay, X belongs to 1 such that X is not equal to 0 and not equal to 1. Is this relation clear? That only 0 and 1 are identified. That is the equivalence relation. Now we have seen geometrically this becomes like this. This becomes something like this, right? So can you topologize this using this topology? This is subspace topology, or that is relative topology of the Euclidean topology or usual topology.
Yes, sir.
So can you topologize this circle?
Sir, in R2, take sir intersection with open disk.
Yes,
Open.
that is okay, but I'm not thinking it as a subspace of R2. Now, can you use this topology to topologize this? I'm thinking this as something like this. There are lots of points, only 0 and 1 are same point. 0 and 1 are identified, except that all those points are different.
But taking inverse image.
Okay, so we'll define something is open here. Okay, if this will be open if and only if the inverse of that will be also that is also open here. So for example, this will be open in the quotient. Okay,
Yes, sir.
but note, you can also note that we already know this zero, something like this, something 0.9, 0.9 comma 1. This is open in the subspace topology, that interval open close 0 1, so it is close 0 1. This is our consideration. So this is open in the relative topology, right? This is open, but the image, yes, but the image, it is like 0 1 is winded like this. Okay, so if we think this as a 0, so the image, it will look like, the image will be like this interval. So image will look like this kind of thing, something like this arc, but one side is closed, one side is open. Now the question, is it open? Is it open in this circle? What is your thought? Yes, this should not be open, right? Our sense says this should not be open because we want this to be a circle. Okay, so that is how the topology will be defined. We'll say something is open here if and only if the pre-image is also open here. So though this is not open, but if we take this thing from here to here, from here to here, this will become from here to here like this. Is it understood?
Yes.
So I am not saying that take image of those open set. That is not how we are defining. Okay, I am defining something to be open if and only if their pre-image is also open. For example, what will be problem if we take this as a open? Then the problem is this is there, but 0 point will also be there, right, in the pre-image. But if you include 0, will it be open in closed 0 1 in the subspace topology? Is it open in closed 0 1?
No.
This is not the case. This is not open. So that is the definition. So the answer is yes. Using the relation, we can define, we can topologize x modulo the relation. So this is also, sometimes this is also denoted by x star in Moncrief's book. That is the notation. So the answer is yes. So u, or let me write v containing this x star or x modulo relation, this is defined to be open if and only if so I am considering this map X, this is our space X, and I am considering the map, the projection. Simply this means X. So consider this map. Let me denote it by P. P sends X to the class of X. For example, in this example, 0 goes to class of 0. Class of 0 means there will be 2 points, right? Right? Something like this. Is it clear? So the only thing is notation. Notation is complicated, but the idea is the obvious one. Idea is clear. There are lots of notation. That's why it seems very complicated. So something is defined to be open in the topology in X modulo relation. Okay, in X modulo relation, if and only if that P inverse of V is open in X. So okay, this way we can generate a topology. Now we need to check that arbitrary union. In this way, arbitrary union will be union. Arbitrary union is also there. Intersection of finitely many open set in this way is also there. We need to check those properties. So you can check that. So this forms a topology. Topology, which is called the quotient topology. So the quotient topology depends on the relation and on the topological space. For example, here you can see those two are same topological space. Those two are same rectangle, same topological space, but we define the relation in a different manner. Here the relation was identified along this side. So this point is identified with this point. Similarly, this point is identified with this point. Okay, point by point. So if that relation is different, then that will give something new. So we'll get a new topology, new space. That's why quotient is important. Quotients allow you to create lots of spaces. Okay. So this is the way to create, but in Munkre's book, it start in a reverse direction, which is very artificial. For first time reader, it will be very confusing. So you should always start in that way. I think this is better way. Lots of books start with this. So now let us define formally. So first we can define quotient map. So this is the whole story, quotients thing. So we also need to identify this X modulo the relation. So this space from picture it is clear this space become a circle, but we need to identify it mathematically, right? So this is the next step how we can identify it. So what is a quotient map? Suppose X is a topological space. Okay, Y is a set. There is no topology. And let P map X to Y. This is a surjective map. Okay. Uh, Sorry. In this case, both are topological space. This is so. This is surjective map is said to be a quotient map if and only if P inverse of U is open. So this is quotient map when P inverse U is open if and only if U is open in Y. So P inverse U, this is open in X. This is true for all U, for all open set U in Y. Okay, if this relation holds, if this property holds for all open sets in U, then we'll call this map a quotient map. Is it clear? So for continuity, we ask that P inverse for open set U, P inverse U should be open. So for continuity, we want this if this is open. But for quotient, we want this to be if and only. So we don't need more than that, right? There are no more than those open sets. Yes. So quotient map always continuous map. Yes, exactly. Great. So this is a note. Quotient map is continuous. So this is quotient map, definition of quotient map. But how will it help? So there are some thing that you should check, that open and closed map. Open map which is continuous and surjective, that will be quotient map. Similarly, closed map which is continuous and surjective will be continuous, will be quotient map. You can check. Those are very easy to check. But let us see how we can define quotient topology. So using this definition, now we can define quotient topology. Okay. So now X is a topological space, Y is a set. Those two things is given, and P map X to Y is a surjective function, surjective map. Okay. Then how do we topologize this space? The same way we'll topologize this Y. Here instead of X modulo the relation, this is some Y and this is some surjective map, right? So put a topology on Y. How we can put? U contained in Y is said to be open if and only if inverse U is open. Okay, this is how we can put a topology on Y. So this Y is said to be a quotient space. Okay, then this Y is said to be a quotient space of X. So it is the generalization of surjective map. So here the interesting thing is that this, if we define Y in this way, then P becomes a quotient map. Okay. So this P is a quotient map. Now, this idea gives a way to identify X modulo the relation. So how do you identify X modulo relation? So let me write that. Let P maps X to Y be a quotient map suppose this is the quotient map. Quotient map means it is surjective and it has the property that something is open here if and only if, sorry, U is open in Y if and only if that P-inverse of U will be open in X. This is the property. So let P be a quotient map. Then the interesting thing is that this map always factors through X modulo the relation. So what is the relation? How do you provide the relation? So we define X related to X dash. So X and X dash to element of X. So X is related to X dash if and only if Px is same as Px dash. So relation is done in each fiber. So take pre-image of a point and all the elements in the pre-image are related to each other. Okay. So the interesting thing is that this kind of quotient map always factors through this map. There exists a continuous map. Okay. This is quotient map. This is given quotient map. This factorization holds for any map, not only for quotient map. This factorization holds for any map. But for the quotient map, the interesting thing is that, so suppose this is P, not P, let me denote it by some F, and this is our quotient map P, then the induced map F dash, if this is quotient map, then F dash is a isomorphism. So this is the interesting thing. Therefore, we can identify X modulo relation with a concrete topological space. So here, that our intuition, whatever the intuition tells, this should be circle, and we can explicitly prove this is the case. Yes, this is true, right? So let me say why this is the case. So consider the map. Oh, sorry. Something is. So that was the example we were considering. So here we have identified 2 points of the interval. So let me consider the space P, which is a map from the interval close 0, 1 to the circle S1. So you, from complex analysis, you know that circle can be thought as a subspace of the complex number, right? Subspace of the complex plane. This is circle. So if you consider the map Pt equal to e to the power 2 pi it, this is actually a quotient map. It need to be proven. It is not immediate that why this should be the quotient map, but let us assume this part. This is a quotient map. Now, can you see what are the point preimage of this preimage of some point? So I am mapping from interval, this 0 1 interval, to this. So let me denote it by f instead of. Can you give me preimage of this points? So can you see what will be preimage of this 0? What will be f inverse 0?
0 and 1.
Exactly, 0 and 1. Because e to the power 0 is equal to 1, e to the power 2 pi I is also 1. Now if
The
so f
preimage
inverse,
of 0 does not exist.
sorry, it is not exist, it should be actually 1, sorry. So you are right, so this is actually 1, I have mistakenly right. So we know e to the power 2 pi I 0 is same as e to the power 2 pi I 1, which is 1. So both 0 and 1 goes to the same point, right? So since this is a quotient map, then this theorem, what this theorem says, that if we take a quotient map, now let us also write, what about something f inverse of z when z is not equal to 1 and z belongs to the circle S1? What will be there? For example, suppose z is taken from here, then what will be the p-image? Suppose this is e to the power 2 pi it, z equal to e to the power 2 pi it, it will take this form, then what will be the p-image? Can you tell me? So this thing is wrapped from this 1 and it ends at 1, right? Now what will be the p-image of e to the power 2 pi it?
T.
T, right? And the interesting thing is there is no other element because it is 0 comma 1. There are lots of pre-image to t plus 2 pi in, but all those elements does not belongs to this 0 1.
Yes, sir.
Sorry, t plus
2
in,
pi
not 2
I.
pi in. T plus in, but only t belongs to that. So thing the thing is actually that this f, by previous theorem, this f actually factors through the quotient, right? This f factors through the quotient space. There exists some kind of map f tilde continuous map.
Yes, sir.
And what is the implication? And moreover, this is not only there exists, this is actually unique map. So let me start with any continuous map, then this kind of factorization exists. What is the meaning of factorization? It means
Partition.
yes, the meaning is that f dash composition p is f, and moreover that theory is slightly more interesting. Moreover, if f is quotient, then that f dash map is isomorphism. Okay, this is the whole theorem. So first,
Sir, isomorphism means, sir?
sorry, homeomorphism. I should not say isomorphism. This is, so I have not defined homeomorphism, but for now you can assume homeomorphism as something. Homeomorphism means topologically equivalent.
Yes, sir.
That as a set, those two things are not only as a set same, but as a topological space, those two are same. You can interchange from one space to another space.
Yes, sir.
Okay, so I will define homeomorphism later, but homeomorphism roughly says from topological perspective, those two things are same. X and y are same. Sorry, here x modulo is same as y.
Yes, sir.
Okay.
Just like in group isomorphism.
Yes. So for set isomorphism, it need to be injective and surjective. But here, continuity is also involved. So there is slightly more
Yes, sir.
things to be added. Okay. So that is what we are getting. That 0, 1 modulo. So the only equivalence class is non-trivial equivalence class is this. So the only relation is 0 identified with 1. This is the only non-trivial relation. Otherwise, x is identified with x. So z is e to the power 2 pi it
Uncle,
quotient.
there is only singleton.
Yes, other singleton element. T identified with t. So I am not writing all those trivial relations. So this F tilde becomes homeomorphism. So the theorem says this 0, 1 modulo the relation, this is nothing but the circle. So geometrically we see that if we identify the endpoints of a thread, that becomes a circle, right? So that is how the idea is mathematically described. So there are lots of things we need to prove, but the idea is clear. Is it?
Yes, sir.
Okay. So tomorrow we'll solve some problem. Not tomorrow. In the next lecture, we'll solve some problem from quotient topology and from others from the
Sir,
next.
can you recommend some book where quotient topology is defined in easy way?
Yes, it is already defined in Munkes, but there is a small book, something small book by Alan Hatcher. You can also look at that book. Uh, General topology, maybe 50 page, those kind of topology by Alan Hatcher. You can search the keyword, you will get the book. There are lots of exercise, beautiful exercise. You need to identify the quotient space.
Yes, sir.
So, is the last step clear?
Yes, sir. Sir, we
Prajna?
need to study homeomorphism, then it
Yes.
will be more clear.
Yes. Homeomorphism should be studied earlier. Otherwise,
Yes, sir.
these statements is not making any sense. But roughly, we assume that homeomorphism is saying those two things are topologically same.
Yes, sir.
Homeomorphism is nothing but there exists a map in the reverse direction. Suppose this map is G, such that F tilde compose G is identity and G compose F tilde is also identity, and G should be continuous.
Yes, sir.
So it means you can continuously move from one space to another. So studying one space is same as studying the another one. Okay, so that is the homeomorphism.
Yes, sir.
Okay, thank you everyone.
Thank
Let
you,
me
sir.
stop here.
Thank you, sir.
Okay,
Thank you, sir. This was quite interesting.
thank you for your patience. Okay, let us stop here.